In previous sections, we've talked about trigonometric identities. Now we're going to talk about solving trig equations. With trig identities, those are true statements for any value that you plug into the equation. With trigonometric equations, you have to find the specific values that work for this equation. So it's a conditional equation. Okay, so what we're going to start off doing is you always want to isolate the trig function and have it set equal to some kind of number on the other side. And that way we can look it up on the unit circle to find what angle would I sweep open so that I get 1/2 on my terminal point for my x value. Now I specifically say x value because we're looking at the cosine of theta right now. So depending on what the trig function is, you're going to be looking at the x coordinate or the y coordinate or possibly both when we're looking at tangent or cotangent. So basically what this equation is asking is for what angle would I swing open and get an x coordinate of 1/2 for my terminal point. So if I look at my unit circle and I look at all the x coordinates of my terminal points, I'm going to get a point up here that's 1/2 square root of 3 over 2. So that would be one place where my x value is 1/2. And that would be when I swing open to 60 degrees. So the other place that I would have 1/2 is when I would get 1/2 negative square root of 3 over 2. And that is when I swing open to 300 degrees. So I have when I open to 60 and 300. Now that's just on the first rotation. So if I asked you to find solutions on the interval 0 to 360 degrees, that's asking for just the first rotation. And my answer to that would be 60 degrees and 300 degrees because that's where my x coordinate of my ordered pair is 1/2. So if I'm asking for all solutions, I have to take into consideration that I can make multiple rotations. If I start at this point here, at the terminal point at 60 degrees, and I add another 360 degrees to that, I'm going to still land in the same spot. I'm still going to have a terminal point with an x coordinate of 1/2. And then I can add another 360 degrees to that. Or I can even subtract 360. Any coterminal angle with 60 degrees would give me an x value of 1/2 of that terminal point. So if I want to list every single possible solution, I need to write 60 degrees plus any multiple of 360 degrees. And n would be in the integer. So it could be -4, it could be -2, it could be +5. I just want to take some multiple of 360. Now, for this point down here, the same thing. I can add or subtract multiples of 360 degrees and still land in the same spot. So any coterminal angle with 300 degrees would give me an x coordinate for my terminal point of 1/2. So when I write down all the solutions that are related to 300 degrees, I'm going to write 300 degrees plus any multiple of 360 degrees. And I'm going to say 360 degrees times n, where n could be any integer, to represent multiples of 360. So if I ask you to find all solutions, you have to take into consideration that you could have multiple rotations and you would still get 1/2 of the x coordinate. If I asked you for just solutions on the first rotation from 0 to 360, then you would just list 60 degrees and 300 degrees. And keep in mind, too, that if I told you to find all solutions from 0 to 2 pi, that's still asking the same thing. I'm asking you to do it on the first rotation, but since I'm giving it to you in radians, I'm expecting the answer to be in radians. Okay, the next example says solve on the interval from 0 to 360 and the interval 0 to 520. So this is on the first rotation, and this would be on the first two rotations, because you're going around twice. You're going 360, and actually I just noticed there's a typo. I want that to be from 0 to 720 degrees, because I want to do that on the second rotation. Two rotations. So it's 360 and then another 360. That should be 720. Okay, so I'm looking to find sine theta is equal to minus square root of 3 over 2. I'm looking for what angle would I sweep open to give me, now I'm looking at the y coordinate of the ordered pair because I'm looking at sine. What angle would I sweep open to get a y coordinate of my terminal point, negative square root of 3 over 2. So if I look at my unit circle, if I come down on the y-axis to about square root of 3 over 2 negative, that would be about right here and here. Okay, so I'm looking at my unit circle. That would be at 240 degrees. If I swing open, that would be 240 degrees. And then if I swing open to this angle, that would be 300 degrees. So on the first rotation, from 0 to 360 degrees, I would have two answers. I would have 240 degrees and 300 degrees. If I wanted to do it on the interval from 0 to 720 degrees, that means I want to add 360. I want to do another rotation. So I want to add 360 to both 240 and 300. So if I take 240 and add 360, that's going to give me a second rotation, which is going to be 600. So I have 240 degrees, and then I have 600 degrees. Our coterminal angles associated with 300 on 0 to 720. I would have 300 degrees. And then if I take 300 and add 360, I'm going to get 660 degrees. So all my solutions on the first two rotations would be 240, 600, 300, and 660. All my solutions on the first rotation would just be 240 and 300. Now the next example, it says find all solutions. And notice this one isn't set up like the previous two where the trig function is isolated. So the first thing we need to do is isolate cosine theta. So I'm going to subtract 1 and divide by the square root of 2. And then when I rationalize negative 1 over the square root of 2, I get negative square root of 2 over 2. If I look at my unit circle, you can look at your reference sheet if you want. That'd probably be the easiest thing to do. And I look to see on my unit circle, where is cosine? So since we're looking at cosine, we're looking for our x coordinate of the terminal point. That would be right here and right here. That would be where this would be negative square root of 2 over 2 on my x-axis. If I look at those angles, and I'm doing this in degrees, this would open up to 135 degrees. And then this would open up to 225 degrees. Since we want all solutions, we want to take into consideration that I could add in multiples of 360 and still land in that same spot so that I get the terminal point with an x coordinate of negative square root of 2 over 2. So I'm going to make sure, since it's asking for all solutions and not just solutions on the first rotation, I want to make sure that I add in the 360 degrees n and the 360 degrees n, where n is in the integers. And that way, we take into consider all of those rotations. Okay, for the last example in solving the basic trig equations, we're going to find all solutions to the equation tangent squared theta. Actually, I'm going to change that to tangent squared theta minus 1, so that way it comes up on the unit circle. We're going to solve tangent squared theta minus 1 is equal to 0. So we first have to isolate tangent. So I'm going to add 1 to both sides and then square root both sides. When I square root both sides, I get tangent is equal to plus or minus the square root of 1, which is plus or minus 1. Now, when we look at the unit circle, there are actually 4 places where tangent is either plus 1 or negative 1. In order for tangent to be positive 1, both x and y have to be the same value, because remember, tangent is the value of the y coordinate over the x coordinate. So in order to get out 1, they have to both be the same. And the place where both x and y are the same would be at pi over 4. That would be the square root of 2 over 2, square root of 2 over 2. And then also at 5 pi over 4. They would be negative square root of 2 over 2 and negative square root of 2 over 2. So if I take y over x in either of those terminal points, I'm going to get 1. So I have that theta could be pi over 4. And since we're saying that it should be for all rotations, in order for me to get any point that lands here or here where I just marked it as red, I just have to add pi, and then add pi again, and then add pi again, and I'll keep landing in those 2 spots. So any multiple of pi would work to get tangent is 1. So I'm going to write pi over 4 plus pi n, where n is in the integers, any multiple of pi. Now, to find where tangent is negative 1, that's where y and x are the same value with opposite signs. So the 2 places that could be, I'll do those in blue, are here and here, at 3 pi over 4 and at 7 pi over 4. At 3 pi over 4, we have the point negative square root of 2 over 2, positive square root of 2 over 2. So when I take y over x, that gives me negative 1. And at 7 pi over 4, I have positive square root of 2 over 2 and negative square root of 2 over 2 for y. So when I take y over x in that case, I also get negative 1 for tangent. Now, for me to land in any of those 2 spots, I just have to keep adding pi, and I keep landing. Since tangent has a period of pi, it repeats every pi rather than 2 pi like cosine and sine. So I'm going to write down for my answer for tangent theta is equal to negative 1, I'm going to write down that it's 3 pi over 4 plus any multiple of pi, where pi is in the integers. So these are all my solutions. There would be 4 of them on the first rotation, but then if we want to get all the rotations and find all the solutions, we would have to add in pi n. Now I'm going to go through some examples of showing you how to solve trig equations by factoring. This to me looks like a quadratic-like equation. If I take out the sign and replace it with x, I get 2x squared minus x minus 1. And that to me looks like a quadratic equation. So what I'm going to do is I'm going to think of this as a quadratic equation and factor it like I normally would, but instead of having x's, I'm going to have signs in there. So when I factor this, I'm going to get sine x minus 1 and then 2 sine x plus 1. You can multiply it back out to check it. Let's do that real quick and I'll just erase it then, so we have room to do the rest of this. So if I take sine x times 2 sine x, that give me 2 sine x squared. And then sine x times plus 1 gives me a plus sine x. And then I get negative 1 times 2 sine x is a minus 2 sine x. And then negative 1 times positive 1 gives me a negative 1. And then if I combine like terms, I get a sine x and a minus 2 sine x. If I combine those, I get a minus sine x. And it works. So it's the same thing as what we have up there. So you can always go back and multiply it through to check to see if it works, if you're not sure you factored it correctly. Okay, once we factor it, then we're going to set each of these mini equations equal to 0, just like we would if it was a quadratic. So I have sine x minus 1 is equal to 0, and 2 sine x plus 1 is equal to 0. So I'm going to get that sine x is equal to 1, and sine x is equal to negative 1/2. Now look at, if you notice, so we know how to write our answer, it's telling us to do this on the first rotation from 0 to 2 pi, and because it's doing it in radians, it's stating that in radians, we want to leave our answer in radians. So when we look at the unit circle, I want to make sure that I write it down in radians. There's only one place on the first rotation that sine, which is my y coordinate of the terminal point, there's only one place where that y value is 1, and that would be at pi over 2. There's 2 places on the unit circle where my angle would give me a y coordinate of the terminal point as negative 1/2. And that would be at 7 pi over 6. If I look at the unit circle, go ahead and look at your reference sheet, and 11 pi over 6. Now, because it's only asking us to find this on the first rotation, we don't have to add in those multiples to make sure we get all the rotations. It's specifically asking us to do this only on the first rotation. So these are going to be our only answers. Okay, for the next example, I have cosine theta sine theta minus 2 cosine theta. This to me does not look like a quadratic-like equation where I can factor it like I did in the previous example, but they do have a common factor. I could pull out cosine theta, and I'm left with sine theta minus 2. Then once I have this factored, I can set each mini equation equal to 0 and solve for each of those. Now you always want to make sure when you have your mini equations that you're not mixing trig functions. When you set up your mini equation, you should only have one trig function in them. So in other words, I shouldn't have cosine and sine in one mini equation. Okay, so if I look at the unit circle, and we're doing this on the first rotation, and we're leaving it in radians, that's according to the directions. It says do it from 0 to 2 pi. So all my answers should be between 0 and 2 pi. There are 2 places on the unit circle where cosine is 0. Cosine is my x coordinate of the terminal point when I swing open. The 2 places, if I look at the unit circle, it's pi over 2 and 3 pi over 2. To solve for sine theta minus 2 is equal to 0, I'm going to add 2 to both sides. And if you notice, this is bigger than 1. This is impossible. This does not exist. My cosine and sine functions have values that are always between and including negative 1 to 1. So this is impossible. There's no place on the unit circle where I would have a terminal point with a y value of 2 because it's a unit circle, so the farthest it can go out is 1 since that's the radius. So for this equation, the only 2 answers I have on the first rotation is pi over 2 and 3 pi over 2. Okay, now in this example, we have 2 sine theta, tangent theta minus tangent theta is equal to 1 minus 2 sine theta. If we're going to solve this by factoring, we always have to make sure that we have 0 on one side and everything else on the other. So I'm going to subtract 1 and add 2 sine theta to both sides. If you notice, we have 4 terms. And when we have 4 terms, the bells should go off in your head and think we're going to do factor by grouping. So I'm going to look at these two and these two temporarily separately. So in the first 2 terms, I can pull out a tangent theta. And what's left would be 2 sine theta minus 1. In the last 2 terms, I can pull out a 1. That's the most that I can pull out, and I would have 2 sine theta minus 1. And these 2 parentheses have to be the same in order for this to work. So I have this and this in common, so now I'm going to pull out 2 sine theta minus 1. And what's left over when I pull out that 2 sine theta minus 1 is tangent theta plus 1. So now I have this completely factored, and I can set up my mini equations. So I have 2 sine theta minus 1 is equal to 0, and tangent theta plus 1 is equal to 0. So I got to isolate the sine theta. So I have that sine theta is equal to 1/2, and I've got to isolate the tangent theta. So tangent theta is negative 1. And then I'm going to solve for each of these mini equations. So I'm going to look at my unit circle, and I'm going to find all the places where sine is equal to 1/2. So there are 2 places that would give me that my y coordinate of my ordered pair is 1/2. That would be at theta is equal to pi over 6, and theta is equal to 5 pi over 6. Now, since the question is asking us to find for all solutions, I need to add in the fact that we're doing multiples of 2 pi as well, because we want to keep going around the circle and land in the same spot and find all the possible solutions. Now, for tangent theta is equal to negative 1, we would put down 2 places. There are 2 places that the y and the x are exactly the same but opposite signs. Because remember, tangent is the y ordered pair, or the y coordinate over the x coordinate. And so y and x have to be exactly the same but opposite signs in order for tangent to be negative 1. So that would be at 3 pi over 4 and 7 pi over 4. And because we want all the multiples of all the rotations, because we're looking for all solutions, I'm going to add in n can be any integer. Now, when you're solving an equation that has a multiple angle, for example, you're trying to find 2 sine of 2 theta. It's not just 2 sine of theta, it's 2 sine of 2 theta. Where it's not just theta or not just x, you have some kind of constant in front of that theta. There are a couple extra steps you have to take for this. So you're going to start off by isolating the trig function just like before. So I have 2 sine 2 theta is equal to 1. So I'm going to divide both sides by 2. I have sine 2 theta is equal to 1/2. So now we're looking to see where double the angle, 2 theta, is going to give me 1/2. So first, let's figure out what angles, since it's labeled as 2 theta, I'm going to label it down here as 2 theta. What angles would give me 1/2 as the y coordinate of my terminal point? That would be pi over 6. And since we're trying to do this for all solutions, we're going to actually add in 2 pi n for all the multiples. And then the other option is at 5 pi over 6. That's where we would have all of our angles that would open up and give us a y coordinate of 1/2 in the terminal point. But because this is double an angle, we want to find the angle now by dividing both sides by 2. So if I divide both sides of the equation by 2, that's going to give me that theta is equal to pi over 12 plus pi n. Because I divide this by 2, I divide pi over 6 by 2, and I get pi over 12. And I divide 2 pi over n by 2 as well. I'm going to divide both sides. That means all the terms on each side. Then I'm going to do the same thing for the next one. I'm going to divide both sides by 2, so that's going to give me 5 pi over 12 plus pi n. This is all solutions. Now, that would be part A. We're finding all solutions. Part B says you want to find the solutions just on the first rotation. So I want anything that falls between 0 and 2 pi, but not including 2 pi. Notice this is an open parentheses, so we're not going to include 2 pi, but everything up to 2 pi. So we're going to do this by using our step in part A, all the solutions. If I let n be equal to 0, and I plug in 0 for n here and here, then I would have, for my answers, I would have pi over 12 and 5 pi over 12. Because I would have 0 times pi, that cancels out, and I'm left with just pi over 12. When I put in 0 for the second n, pi times 0 is 0, and 0 plus pi, 5 pi over 12, is 5 pi over 12. These two values are definitely on the interval 0 to 2 pi. So now let's try n is equal to 1. If I plug in n is equal to 1, I'm going to have pi over 12 plus 1 pi. And if I add pi over 12 and 1 pi, that's going to give me 13 pi over 12. And if I take 5 pi over 12 and I add 1 pi, that's going to give me 17 pi over 12. For n is equal to 1, the 13 pi over 12 and the 17 pi over 12 is still within 0 to 2 pi. So let's go further. Let's see if we can do n is equal to 2. If I plug in n is equal to 2, now I'm adding 2 pi to pi over 12. And when I add 2 pi to pi over 12, I'm going to be going over the first rotation because that's going to be more than 2 pi. So I'm going to stop here and I'm going to say that my solutions that are on just the first rotation, 0 to 2 pi, I have 4 answers: pi over 12, 5 pi over 12, 13 pi over 12, and 17 pi over 12. So these are specific to just on the interval 0 to 2 pi. In part A, we found all the solutions. So these would be all the solutions. Now, if you're not comfortable with this and you want to convince yourself that this works, you can plug in pi over 12 into our original equation and see if it works. So if I put in pi over 12 in for theta, I would get 2 times sine of 2 theta, so 2 times pi over 12, which would be pi over 6. Sine of pi over 6 is a half, so I would have 2 times a half, and then I would get 1, so it works. And you can try that with each of those values to make sure it works, if you want to convince yourself that it's true. Okay, the next example, we have tangent of theta over 4 is plus the square root of 3 is equal to 0. Okay, so the first thing I want to do is I want to subtract the square root of 3 from both sides. And then I want to solve for theta over 4 for all solutions. So what angle would give me negative square root of 3 on the unit circle? That would be where the y over the x is negative square root of 3. Well, that would be 2 pi over 3 plus 2 pi n. Actually, what we could do, instead of writing it out separately, we could just write it, because it repeats every pi, I could write it as 2 pi over 3 plus pi n, and that would get all of my possible solutions in there. Because if I go around the circle, the two places that it would be 2 pi over 3 and 5 pi over 3. But if I keep adding multiples of pi, that's going to include anything that involves 5 pi over 3. So let's just leave it like this to make it a little bit easier. Okay, now I want to isolate theta. So I'm going to multiply the whole equation by 4. That theta is equal to 8 pi over 3 plus 4 pi n. So this would be for all solutions. If I want to check it on just the first rotation, so just on 0 to 2 pi, then I can just start plugging in values for n and see what I get. Well, if I plug in n is 0, that's where I'm going to start. I'm going to plug in 0 for n here, and then I'm just going to get 8 pi over 3. Now, if you notice, even though I plugged in n is 0 and I get 8 pi over 3, this is already over 2 pi. 8 over 3 is much bigger than 2, so this is over 2 pi. So I'm not even going to go ahead and try to plug in n as 1. That's just going to make it bigger. Even n is equal to 0 is too big. So in this case, there's actually no solution on the interval 0 to 2 pi. There's plenty of solutions, but there isn't any on the interval 0 to 2 pi because everything we would plug in for n would make it bigger than 2 pi. It's past that first rotation. My last example for going through equations with multiple angles, I have 2 cosine 3 theta is equal to negative square root of 2. I want to isolate the cosine 3 theta, and I'm going to divide both sides by 2. So to solve for 3 theta, I want to find the two places on my unit circle in which my x coordinate, since this is cosine, my x coordinate of the terminal point is negative square root of 2 over 2. And those two places are 3 pi over 4 and 5 pi over 4. Okay, now I'm going to divide everything by 3, and I'm going to get that theta is equal to pi over 4 plus 2 pi n over 3, because I have to divide everything by 3, and then 5 pi over 12 plus 2 pi n over 3. So this would be all solutions. If I want to find it now specifically for the interval 0 to 2 pi, I have to start plugging in values for n and make sure that I do not go over 2 pi. Okay, so when n is 0, I'm going to get pi over 4 and 5 pi over 12. When n is equal to 1, I'm going to have pi over 4 plus 2 pi over 3. And when I find a common denominator and add that, I'm going to get 11 pi over 12. Now for the second one, I'm going to have 5 pi over 12 plus 2 pi over 3, because I'm plugging in n as 1. That's going to give me 13 pi over 12. Now, these are still within 2 pi, so now I'm going to try n is equal to 2. For n is equal to 2, I'm now going to plug in 2 for n, and I'm going to get pi over 4 plus 4 pi over 3. Because I'm plugging in 2 for n, I'm going to get 2 times 2 pi, which is 4 pi in the numerator. So now I'm going to use common denominators and all that stuff to add pi over 4 plus 4 pi over 3, and I'm going to get 19 pi over 12. When I plug in 2 for this n, I get 5 pi over 12 plus 4 pi over 3, and that's going to give me 7 pi over 4. When I do n is equal to 3, then I'm going to get 6 pi over 3, which is 2 pi. And I'm going to plug in n is 3, and I'm going to get 6 pi in the numerator, divided by 3 is 2. So I'm going to have 2 pi. And when I take 2 pi and add it to something, that's going to go over 2 pi. So this is where I need to stop, because then it's going to go outside the interval of 0 to 2 pi. So on the first rotation, these are my 6 answers to solve 2 cosine 3 theta is equal to negative square root of 2. In the next set of examples, I want to show you how you can use identities to make substitutions so that you can solve for trig equations. Now, when you're solving for trig equations, you basically want to make sure that your equation has all signs in it, or all cosines, or all tangents. You want all the same trig function. And if it's not, you have to find a way to make a substitution or factor it so that you can make separate equations with just one function in it, or find a way to make a substitution so that you will have all the same trig function. So in this case, we're going to use trig identities to substitute in to create it. So to create an equation that has all the same trig function in it. And if you recall, we have the Pythagorean identity secant squared minus 1 is equal to tangent squared x. So what I'm going to do is I'm going to use this Pythagorean identity to take tangent squared x and substitute in secant squared x minus 1 so that I have everything in terms of secant. So I'm going to replace tangent squared with secant squared theta minus 1. Then I have the minus 2 secant theta is equal to 2. So now I have everything in terms of secant because I made that substitution. So I am now going to get everything to one side and try factoring. So if I subtract 2 from both sides, and I put it in descending order, I'm going to have secant squared theta minus 2 secant theta minus 3. And now I can factor this as if it was a quadratic. This is a quadratic-like equation. Okay, so I have secant theta and secant theta here. So when I multiply them, I get secant squared theta. And I want to find the factors of negative 3 that would add to give me negative 2. So that's going to be a minus 3 and a plus 1. So now what I'm going to do is I'm going to make my mini equations. I'm going to have secant theta minus 3 is equal to 0. And secant theta plus 1 is equal to 0. So I'm going to add 3 to both sides. And over here, I'm going to subtract 1 from both sides. Now, this isn't something that's on our unit circle. So we would have to use inverse secant. And when we did that, we would get the theta is equal to, if we do this in radians, 1.23 if we round to 2 places. This is on our unit circle. Remember, secant and cosine are reciprocals. So where is cosine negative 1? Because negative 1 and negative 1 are reciprocal. So where's cosine negative 1? That would have to be pi. And if we want to do this, on the first rotation, 0 to 2 pi, I don't have to add in the plus 2 pi n. This would be where we're done. And you can always plug back in and check to see if you've got it right. Okay, in the next example, we have to find for all solutions of theta, where we have cosine of 2 theta is equal to 3 sine theta minus 1. Now we want to make sure, since we have two trig functions here, cosine and sine, we want them to all be in terms of cosine or all in terms of sine. We also want to make sure that we have the same angle, that they're all thetas or all 2 thetas. And since we're practicing using substitutions right now, using trig identities and substitute, I'm going to look at my double angle formulas for cosine and try to make a substitution. I want to find a substitution that has all sines in it. So if I think back to my double angle formulas, I have a formula that is equal to 1 minus 2 sine squared theta. So I'm going to replace cosine 2 theta with 1 minus 2 sine squared theta, and then I'll have everything in terms of theta and everything in terms of sine. Now I'm going to move everything to one side and set it equal to 0 so we can solve by factoring. So I'm going to subtract 1 and add 2 sine squared theta to both sides. And while I'm at it, I'm going to put it in descending order as well. So now I have everything on one side, 0 on the other, and I can factor this as if it was a quadratic. Okay, so to factor this, I want to find, let's see, I'm going to get 2 sine theta minus 1 and sine theta plus 2. So when I multiply that back out, I'm going to get 2 sine squared theta plus 3 sine theta minus 2. And if you want to convince yourself that that works, go ahead and take a minute, pause the video, and you can multiply it back out to check it. I'm going to set each mini equation to 0. So I have 2 sine theta minus 1 is equal to 0. And I have sine theta plus 2 is equal to 0. So I'm going to get that sine theta is equal to 1/2. And I'm going to get that sine theta is equal to negative 2. Looking at this, right away I can see this does not exist. There is no possible solution for that. Because remember, sine and cosine are the x and the y coordinates on the unit circle, and since it's a unit circle, the biggest that could be is a positive 1, or the smallest it could be is a negative 1. So sine of theta is equal to negative 2 is impossible. However, there are 2 places on the unit circle where theta could be 1/2, and that would be pi over 6 and 5 pi over 6. And since this question is asking us to find all solutions, I want to make sure I add in all the possible rotations. So I'm going to add in plus 2 pi n, where n is an integer. So my solutions for this equation is going to be pi over 6 plus 2 pi n, and 5 pi over 6 plus 2 pi n. For the next example, we are going to solve this just on the first rotation. And notice that the interval that's given to us is 0 to 360 degrees. So this question is asking us to do it on the first rotation and answer in degrees. So for this one, we're going to use our sum to product formula, where we have sine of x minus sine of y is equal to 2 cosine of x plus y over 2 and sine of x minus y over 2. So we're starting with sine of 5 theta minus sine of 3 theta is equal to cosine of 4 theta. Now think of this is my x and this is my y, and I'm going to do some substitutions here. Using our formula, I'm going to have 2 cosine of x plus y, which would be 5 theta plus 3 theta, which is 8 theta, divided by 2, that's going to give me 4 theta. And then I have times sine of x minus y over 2, so that's 5 theta minus 3 theta, which is 2 theta, divided by 2, which is just theta. So now I'm going to subtract everything to one side and factor. In both terms, I have cosine of 4 theta. So I can factor out the cosine of 4 theta, and I'm left with 2 sine theta minus 1 is equal to 0. So now I'm going to set up my 2 mini equations. I have that cosine 4 theta is equal to 0, and I have 2 sine theta minus 1 is equal to 0. Well, this second mini equation tells me that sine theta would have to be 1/2. And on the first rotation in degrees, because that's what this question is asking us to do, the places that my y coordinate of the terminal point when my angle sweeps open to be 1/2 would be 2 places. It would be pi over 6 and 5 pi over 6. So these are the 2 answers for the second mini equation. Now for the first mini equation, I'm looking for angles that would sweep open and give me an x coordinate of 0 for my terminal point. And so that would give me pi over 2 and 3 pi over 2. But I have to solve for theta, so I have to divide both of those by 4, and that would give me pi over 8 and 3 pi over 8. So these are the 2 answers for the first mini equation. And you can always go back in, plug those values in to check if you want to verify that they work. Okay, last example, we're going to use the sum and difference formulas. If you recall, the difference of angles for cosine formula, S minus t would be cosine S cosine t plus sine S sine t. And that is exactly what we have right here. Think of this as your S and this is your t. So I'm going to rewrite this as cosine of S minus t. S is 2x and t is x. So I have cosine of 2x minus x, which is x. And now I'm looking for an angle. When I sweep open, I get a terminal point that has an x coordinate of positive 1. And the only place that that would happen would be at 0 degrees. And then since this is asking for all solutions, we want to make sure that we add in the 360n multiples of 360 so that we get all of those rotations in. So any multiple of 360 is going to work here.